So our lesson on 4-8 is going to be split into 2 days. Today, all I'm going to have you guys do is familiarize yourself with the complex number system and what a number in complex form looks like. And then we're going to do the manipulation and arithmetic with complex numbers. So we're going to add, subtract, multiply, divide, and simplify complex numbers. So Descartes, all his work with complex numbers, it all was based off of one assumption that you have to accept in order to move on. But we decided we're going to go ahead and accept it because imaginary numbers actually kind of rock. This is how electronics are capable of working. So his assumption was, if you let the square root of -1 be represented with the letter I, all of a sudden a bunch of doors opened up. Let's look at this. What if I squared both sides of this equation? What would happen if you squared the square root of -1? They'd cancel out and you get -1. And then what happens over here on the right hand side? I squared. So there are two assumptions that we have to work with today. Anytime I see an I squared, I'm going to replace that with the number -1. And that's because the square root of -1 equals I. So let's talk about this. Up until today, you guys were not capable of simplifying that radical. But now we can, because this is really the square root of 4 times the square root of -1. Can you guys give me a better name for the square root of 4? 2. And now you know a better name for the square root of -1. I. So if I asked you to simplify the square root of -4, you would say it's 2i. So what about the square root of -12? This one's a little more difficult. This time I'm going to break it into 3 radicals because I'm going to have the perfect square, I'm going to have the -1, and then I'm going to have the leftovers in the last radical. What's a perfect square that's hiding inside of 12? 4. And then what's the leftover? Now what do you think I put in the middle? The -1. So can you guys give me a better name for the square root of 4? 2. Give me a better name for the square root of 1? The -1? I. And then square root of 3 is just simply square root of 3. So the square root of -12 breaks into 2i square roots of 3. And this one always throws kids, and there's a couple on your homework where they ask you to simplify something like this. Square root of -7. Are there any perfect squares inside of 7? No. So all you're really doing is you're breaking this into the square root of -1 times the square root of 7. Well, guys, give me a better name for the square root of -1. I. So I would accept the answer of I times the square root of 7. Or some books, I don't know what your book does, I haven't looked at it that closely. Some books put the I after the radical, so they put like square root of 7 times I. What you cannot do is have that I sit inside of the radical symbol. It has to be out of the radical. So we'll practice more of this later. All right, let's talk about how we are going to do arithmetic with complex numbers. A complex number is in the form a plus bi. This is called standard form of a complex number. And every time we do work with complex numbers, you have to reduce it all the way until you get it to look like that, standard form. So my first question is, I have the complex number 3 minus 1i, and I'm going to add it to the complex number 2 plus 3i. Every complex number has a real component and an imaginary component. So the problem says, go ahead and put circles around the real parts. Which numbers here do you think are the real components? The ones that are not imaginary. So the 3 is a real component, and the 2 is a real component. So what do you think is a complex or an imaginary part? The thing with the I. So I have a -1i, I have a plus 3i. So if I try to add the real parts together, that's the same thing as saying 3 plus 2. And if I try to add the imaginary parts together, that's saying -i plus 3i. Well, go ahead and simplify that for me, ladies and gentlemen. 3 plus 2, better known as 5. And then what would happen with -1i plus 3i? It would be positive 2i. Yep, they're almost like variables, like an x. But they're really not. Now, you don't have to show work when it comes to adding complex numbers together. You're probably going to do a lot of that work in your head, but these are your notes, so we want to illustrate what we did. Adding is a little boring. Multiplying is a little more exciting. So when I see a complex number times another complex number, it almost represents a binomial times a binomial that we used to do, and that's exactly how we're going to approach them. They're a distribution problem. They're a FOIL problem. So we start with the first part of FOILing, which says to take 7 and multiply it by negative 4. So what's 7 times negative 4? It's negative 28. And then outer would be 7 times 9i. So that's plus 63i. And then negative 3i times negative 4 would be a plus 12i. And then finally a negative 3i times a positive 9i is a negative 27i squared. Now, you are not done until your answer looks like a plus bi. Does your answer right now look anything like a plus bi? Not even close. So that means we have a lot of simplifying we have to do. Do you see any like terms right now that I could collect together? Yeah. These little red guys here in the middle, those are like terms. So let's go ahead and collect those together. So I have negative 28, and if I add those together, I get a plus 75i. And right now, I still have a minus 27i squared. Well, I still don't look like a plus bi. There must be something more I can do. If I go back a few screens, oops, too many. What did we say I squared was equivalent to? What does it say right here? I squared is really a negative 1. So that means when I go back to this problem, anytime I see an I squared, I could replace it with a negative 1. So this is really like negative 28 plus 75i. What would happen if you took negative 27 and multiplied it by a negative 1? It'd be a positive 27. Yeah. Almost there, guys. One more simplification you can do. Now you have real numbers that you could combine together. If I add negative 28 plus 27, I get negative 1, and then I still have the plus 75i. Is that now in this complex form, a plus bi? It is. Can you tell me what your real part is? Which one of these is the real part? Negative 1. Which one is the complex or imaginary part? 75i. Good, good, good. All right, let's practice this a little bit. They're going to go between adding complex numbers together, subtracting, multiplying. Sometimes they combo them all together. So when I look at number 1, I have 2i, and I'm trying to add it to the number negative 4 minus 2i. So the first thing I do is I'm looking for real parts to add together. Well, it turns out this is the only real part to the whole equation, or the whole setup. So we have negative 4. And then my complex, or I should say imaginary parts, I have a positive 2i plus negative 2i. What happens when you try to combine positive 2i and negative 2i? They cancel out. So you could write plus 0i. That would be an acceptable answer. But what do you think is the more common version of this answer? They just write negative 4. Yeah, if you don't have an imaginary component, you don't have to put plus 0i. So that was a case where I took two complex numbers, and I added them together, and I produced a real number answer. Number 2, be careful. This time there's a multiplication problem, because there's no symbol in between, so we assume they mean multiplication. So we're going to start with 3 times 2, which is 6. And then 3 times I is positive 3i. 1i times 2 is positive 2i. And then I times I will be a plus I squared. This is nowhere close to done, because you're not done until you can whittle it down to a plus bi form. So first thing I notice is we've got some like terms here in the middle I could collect. And I know some of you are really itching to skip steps and just jump to this final answer. I would tell you I'm hesitant to allow you to do that, just because I know when kids do that, they usually mess up. The other thing you're going to have to fix here for me, guys, is what is I squared equal to? It's a negative 1. So adding a negative 1 is the same thing as subtracting 1. So final answer. If I combine my 6 and negative 1 together, I get 5. And then I still have a plus 5i. Questions so far? All right. One more FOIL problem here, number 3. 4 times 1 is a 4. 4 times 2i is a plus 8i. inside 3i times 1, so plus 3i. And then last, 3i times 2i is a plus 6i squared. So we got a little bit of simplifying to do here. You guys are going to add together your i's in the middle. And you're also going to replace the I squared with a negative 1. So instead of plus 6i squared, what happens to this last term? It becomes a 6 times a negative 1. Give me a better name for 6 times negative 1. Minus 6. So final answer. If I combine the 4 and the negative 6, I get negative 2 plus 11i. All right. Questions so far? I'm going to pause the recording. So here on number 4, you guys were supposed to distribute the 3i. And I saw a lot of good stuff here. You ended up with 3i and then minus 6i squared. And this is where I saw some mistakes happen. We know we're supposed to replace an I squared with a negative 1. So unfortunately what I saw when I walked around was some of you did replace it with a negative 1. But you also randomly kept an I there. Remember, it's substituting in for a negative 1. So this is really 3i. And then negative 6 times a negative 1 will change this to a positive 6. That turns into a real number component. There's no longer an I with that number. But the best possible answer you could have given me was if you flip this around and you put it in a plus bi form. It's not wrong if you didn't flip it around. It's just not proper. So keep that in mind. So same thing here on number 5. We're going to distribute a 3i. So we have 12i minus 3i squared. So once again, instead of I squared, I'm going to replace I squared with a negative 1, which changes this to a 12i. This will become negative 3 times negative 1, so it's a plus 3. There's no longer an I with that term. And then best possible answer is if you flip this around and you write 3 plus 12i. And then number 6 is kind of a disaster, simply because there's a lot going on. So you've got real components and complex or imaginary components. So I'm going to start with the real components. I have a 3, and then be careful, you're subtracting a negative 2. So that's really like adding a 2. And then later on, we're adding a negative 5. So that's subtracting a 5. So if I combine all those real components together, 3 plus 2 minus 5, they end up canceling each other out to a 0. If you didn't write the 0 down, that's fine. As far as the imaginary components go, be careful here, guys. You are subtracting a 3i. So that's subtract 3i. And then later on, we're adding the 1i. So if I combine my imaginary components, I get a negative 2i. But once again, rarely will they say 0 minus 2i. Most of the time, they'll just say your answer is a negative 2i. Questions regarding those 3? All right, let's try 3 more then. I'm going to pause the actual video. So on number 7, saw y'all distributed the 4i. Which ended up being 24i, minus 8i squared. And then we remember anytime we see an I squared, we're going to replace that with a negative 1. So this is really 24i. Negative 8 times a negative 1 would turn into a positive 8. And again, if you left your answer like this, you're not wrong. It's just more proper to flip it around and put it in a plus bi form. When you hit number 8, we are adding 2 complex numbers together. So you're going to add the real components, and then you're going to add the imaginary components, and you're going to write a simplified answer. So 5 plus negative 2 is 3. And then positive 6i plus the 4i should be a plus 10i. And number 9 was not meant to be tricky, so I hope you didn't overthink it. We're just distributing a 9 into a complex number. This is actually really easy because nothing simplifies. It just becomes a 99 plus 45i. And since there's no I squareds in this statement, this is the answer. It's in a plus bi form. We're done. All right, do they move on to division after that? Yeah. All right, before I talk about how we divide complex numbers, I want to have a little review about a couple of different factoring and FOIL problems. So if I asked you to FOIL out x plus 2 times x minus 2, you should be very happy because this is actually one of the easiest FOIL problems I could give you. You would do x times x and get x squared. And then on the outside, you'd get a minus 2x. On the inside, you'd get a positive 2x. And then for the last terms, you'd get negative 4. Now, what's going to happen when you try to simplify any like terms here in this final solution? The positive 2x and negative 2x will cancel each other out, and we're just left with the polynomial x squared minus 4. So we've been working a lot with factoring, where I would give you x squared minus 4, and you guys would have to go backwards and factor it into x plus 2 times x minus 2. We called that the good twin, evil twin question. Turns out when you're factoring good twin, evil twins together, math works out beautifully. So a very similar problem. What if I gave you x plus 3 times x minus 3? And I wanted you to FOIL it out. Well, I do x squared. Should I even bother doing outside, inside? No, because they're just going to cancel out. So I'm going to go first, skip outer, inner, and then the last is x squared minus 9. These are fancy terms coming up here, guys, okay? What we just did was we multiplied by the conjugate. So don't confuse that with conjugate from Spanish class. The conjugate in math is the good twin versus the evil twin. And mathematically, the reason conjugates are so neat is because they end up giving you half the work, because they cancel each other out in the middle. So little bit of an aside here. Back in geometry, and we did this a few days ago as well, if I had 2 over the square root of 3 as my solution, did I allow you to leave your answer like that? No, we said we had to rationalize the denominator. So what we had to do is we multiplied top and bottom, numerator and denominator, by the square root of 3. And that was the equivalent of multiplying by a 1 for the whole fraction, so it didn't screw anything up. And we'd end up with 2 square roots of 3 over 3. So this is what we called rationalizing the denominator. The reason we had to rationalize the denominator is because someone in history, many years ago, said it was not acceptable to leave a radical in your denominator. I don't know. I don't know the answer to that. It is stupid. I agree. I'm sure there's a reason. I just haven't stumbled upon it. So I have an issue. What if I gave you that? Now to you guys, you probably think, that looks great. Leave it. Because it looks nice and concise, right? Well, to a mathematician, this is improper. What is I equal to? Look at the very beginning of your notes. It's the square root of negative 1, right? So now that I remember I is the square root of negative 1, does that look pretty anymore? No, in fact, it looks downright evil. We're not allowed to leave radicals in the denominator. So when you see a division problem with i's, where there's an I in the denominator, you cannot leave your answer looking like that. So what we're going to do today is we're going to use what's called the complex conjugate of the denominator. So if your denominator is something that looks like this, a plus bi, his complex conjugate is just a minus bi. It's the good twin, evil twin. Now sometimes you have the evil twin and you want to give the good twin. So in order to divide a complex number, we're going to use the complex conjugate in order to simplify the denominator. This is the only mathematical way we can manipulate it so that we have a proper proper complex number answer. And I'm sure you've guessed by now, but when we're done, every single answer will look like that, a plus bi. So let's take a look at this first example. It says 4 plus 5i divided by 2 minus 1i. Is it okay if I just leave my answer like this and run away? No, because I is in the denominator, and we just decided that was improper form. So what we're going to have to do is realize that 4 plus 5i is a number, and 2 minus i is a number. And I want you to try to identify the complex conjugate of your denominator. Anyone think they know what that is? The complex conjugate of 2 minus I. It's going to be 2 plus I. So it turns out we started with the evil twin, and now I'm going to give you the good twin. So I need each twin. The idea is the real part stays the same, but the complex part, the imaginary component, you have to reverse the sign. So what we're going to do now is we're going to multiply both the numerator and the denominator by that complex conjugate. So down here, write kind of small, guys, and start way over to the left. You've got 4 plus 5i over 2 minus I That's my original problem. And we're going to multiply both the numerator and the denominator by 2 plus I. All right. You're not going to like this one, okay? You're going to have to multiply the numerator out. This is a FOIL problem. And then you're going to have to multiply the denominator out. That's another FOIL problem. All right, let's concentrate on first the numerator. The numerator says 4 times 2 is the first part of FOILing. So 4 times 2 is 8. 4 times I is plus 4I. 5I times 2 is plus 10I. And 5I times 1I is 5I squared. Whew. That's the numerator. Let's talk about the denominator. Don't even simplify yet. We'll get there. In the denominator, I'm going to FOIL 2 minus I times 2 plus I. So 2 times 2 is 4. 2 times I is positive 2I. Negative I times 2 is negative 2I. And then negative 1I times positive 1I is negative I squared. Okay, that looks like a big old mess. We have a lot of simplifying to do because remember how I said you're not done until your answer looks like that? I mean it. You're not done until your answer looks like that. So start up in the numerator with me, guys. Are there any pieces of the numerator that would combine together? The 4i and the 10i in the middle? So let's rewrite that numerator as 8 plus 14i. Go ahead and keep it as plus 5i squared for now. All over. What happens in the denominator for those like terms right here? They're just going to cancel out. So my denominator is still a 4 and then a minus I squared. Okay, I still don't look like a plus bi. So there must be more simplifying happening on. The I squareds are all going to get replaced with negative 1s. So this I squared and this I squared are going to get replaced. So down here you're going to need some more space. Rewrite it as 8 plus 14i. And then instead of plus 5 times I squared, what does that become? A minus 5, thank you. Over. In my denominator, 4. And then what's going to happen with a subtract negative 1? It becomes a plus 1. All right, we're almost there, guys, promise. Up in your numerator, do you see some like terms? I have an 8 and I have a minus 5. That's really a 3. And look how pretty the denominator came out. Your denominator's a 5. And you'd think you're done, right? Still not done. Your answer is supposed to look like A plus BI. So I have to separate this division problem. When I divide a quantity by 5, that means I'm actually dividing every term in the numerator by a 5. So this is really 3/5 plus 14/5 I. Now do you look like A plus BI? Yeah! Alright, how fun was that? Super fun, Abruzzo. I think I could say with confidence your least favorite problem today was division. Don't worry, we're not done. We'll do more. Yes! Let's talk about just identifying conjugates. Complex conjugates. Anyone think for number 10 they can tell me what the complex conjugate is for 1 minus 2i? 1 plus 2i, good. How about number 11? What's the complex conjugate for 3 plus 5i? 3 minus 5i? And this one's a little tricky. Do you know what we could use as a conjugate for I? Most kids say negative I. Turns out you could just use I. You don't have to worry about negating it because there's no real part, so you don't have to cancel anything out. So there's one on your homework where like the denominator is a 5i. I don't know what the numerator is. So I'm going to give you a little hint. You can just multiply top and bottom by I, and that'll do the trick. What's the complex conjugate for 3 minus 1i? 3 plus 1i. Very good. All right, the identification of the conjugate is actually one of the hardest parts for kids. The rest of it, while it's not terrible, it's just a lot of busy work. Again, I want to warn you, do not skip steps with simplifying. That's when mistakes happen. You guys are too new to this to skip steps. Obviously, these have a ton of work. Please show your work. All right, let's try number 16 together, guys. What is the complex conjugate of your denominator of 1 minus 2i? I heard 1 plus 2i. Thank you. So let's multiply numerator and denominator by 1 plus 2i. Now, it turns out this one's not too bad. The numerator, for instance, I'm just distributing a 3i, so there's going to be a lot less to the distribution than my previous problem. 3i times 1 is a 3i. And 3i times 2i is a plus 6i squared. I know that simplifies. Just hold your horses. We'll talk about that one in a second. As far as my denominator goes, here I will let you skip a step. What's always going to happen when you multiply your conjugates together? The first term will be 1 times 1, 1. What happens with the outer inner? They cancel out. That's the whole point of the conjugate. So if you recognize, ooh, they're going to cancel, don't even write them down. But negative 2 times positive 2 is a negative 4i squared. Okay, still not done, because all these I squareds are going to get replaced with negative 1s. So this numerator becomes a 3i, and then 6 times negative 1 is really a minus 6. And then this denominator is really a 1. Negative 4 times negative 1 is going to turn into a plus 4. So your denominator is really a 5. Now this is where it gets kind of tricky. I want this written in a plus bi form. So I need to reverse the order of my numerator, and I need to divide both of them by a 5. So it's negative 6/5 positive 3/5 I. Division is the least favorite arithmetic operation for most things, i's included. And 18, even though it looks weird, it's actually really easy, guys. Anyone catch what I said to multiply 18 by? Yeah, just multiply by I top and bottom. So the numerator becomes a 2i plus 2i squared. The denominator becomes an I squared. And we know we're supposed to replace I squareds with negative 1. So this becomes a 2i. 2 times negative 1 is really a minus 2. All right. If you left your answer like this, like on a test or quiz, I'd be okay with it, but this is technically not in a plus bi form. First thing I notice is I'd have to reverse the order, and I'd have to distribute a negative 1 to each fraction. So it's going to become a positive 2 minus 2i. Yuck. All right, we're going to pause the lesson there.